This video obviously is going to have everything to do with what I call the dreaded carbocation rearrangement. If you go back to the very last video lecture, which by the way I would definitely suggest you look at before you look at this video, otherwise you'll be incredibly confused. We talked about this intermediate, or this idea of kind of a resting state for a reaction, kind of a high energy resting state before it goes through and does product formation. It turns out that that carbocation that we talked about, that carbon with a positive charge or a deficiency of electron density, it has some problems with this rearrangement. So what we're going to see in just a second is that it kind of looks like that simple reaction, that simple addition of the hat across the double bond of the AB system is going to start to look a little bit stranger. Right? And so the first thing I want to kind of review with you is just the kind of the normal reactions we talked about, and then hopefully we'll kind of build in this picture of different types of carbocation rearrangements. All right, so here are a couple of kind of predict the product type questions that we should start to feel comfortable with. I added a little bit extra to these questions. One of the things you'll notice is, of course, we have an alkene. That's the only thing we know how to do anything with at this point. So that's pretty much the only type of starting material that I'm allowed to ask you about. You'll notice the HI, right? This is that HX addition reaction that we talked about. And one of the things that you'll notice that I included here that I didn't include in the last video is this thing called the solvent, right? So solvent is kind of one of these things that sometimes confuses students. Quite often it confuses students. The good thing to keep in mind is that it's not usually involved in the reaction. It's just kind of a little bit of a smokescreen to try to screw you up a little bit. And keep in mind that usually what you list here on the reagent side are the kind of the reagents that actually react with the starting material and some of the conditions that you might be employing to actually carry out the reaction. So for instance, this guy is just included as an organic solvent, and as we kind of go through the term, we'll start to see more and more of these solvents and kind of be able to recognize when it's a solvent and when it's actually involved in the reaction. So this is methylene iodide, right? It doesn't really matter. There's methylene chloride. There's all kinds of different solvents that are going to do similar things. THF, tetrahydrofuran, is another really common solvent. And keep in mind that solvent's just something that we can dissolve all the kind of reacting parts in. So those two things don't actually participate in the reaction. As you might expect, right, when you look at this thing, what our job is when we do an alkene addition is to add across the double bond with whatever that A and B happens to be. So here is our A and our B. And then you'll notice here that I purposely chose an alkene that had a difference in substitution. And if you remember the Markovnikov video, the previous one to this, what's going to happen is the H will add to the less substituted of the two carbons, and then the kind of the meteor part will add to whatever the more substituted carbon is, right? And so this is a perfect example of kind of a predict the product kind of thing that you should start to feel comfortable with. So you could just answer this by saying that all these things that don't change are going to look like this. The iodide is going to pop on there. And often, unless you're actually talking about a reaction mechanism, usually you kind of leave the hydrogen off that was added there. So I'm going to start to do that a little bit more, unless it happens to be important, in which case I'll definitely highlight it. Similarly, this guy, right, we've got HBr, right, and so there's our AB system, and it's going to add across this double bond, and we can see here that one of these carbons is a little bit more substituted. So the Br is going to add to the more substituted carbon in this case. And so we've formed these two different alkyl halides, and probably at this point you're feeling really, really good, right? Well, the job of an organic chemist is to make you feel like you haven't learned anything, and when you feel like you've learned something, I'm going to try to confuse you because I'm a big jerk that my mom didn't hug enough. So I'm going to put another example up here, and you're going to probably notice a pretty surprising thing has happened. I'm going to take this starting material, and I'm simply going to remove this group right here. And kind of oddball thing happens. Okay, so I just removed that one methyl group, right? And if we're just kind of being the mindless automatons that we sometimes are, we'll say, oh, well, that HI is going to add across that double bond. That's still a more substituted carbon right here, so the H is probably going to go here. And so you do the predict the product game. You go through and you say, well, this is going to be the product that I suspect is going to pop out of that thing. And then you get your exam back, and this happened to me all the time, and you see this big giant X with a -5 or something like that. And you say to yourself, I thought I understood this. Well, it turns out you understand it pretty well, but there's one additional step to this mechanism that we have to consider. It actually turns out that the true product that pops out of this thing is what's called a rearrangement. And the iodine actually ends up right there. And you might say, well, that kind of goes against everything that he was just talking about in terms of adding across the double bond. You know, there's how did that iodine get there, right? I know that there's a hydrogen there. Like, where did that hydrogen go? So the answer is to look at the mechanism. And so that's what this very next thing is going to hopefully show. Okay, so we're going to do a mechanism here to explain this kind of oddball product where the iodine kind of popped onto a carbon that didn't even have a double bond present. So the important thing to recognize about all that we learn in organic chemistry is we usually start with kind of a reaction, a foundational set, and then we add curveballs to it. So this is going to be a curveball on that normal reaction mechanism that we talked about before between this thing acting as a nucleophile on that electrophilic HI. So first, let's show our HI with all of its electrons there. And I'll try to make my mechanistic arrows red. And so, just as normal, we expect the bond to swing one of either of two ways. And the way that it's going to swing is going to make sure that whatever that carbocation that initially forms is actually forming on the more substituted carbon. So in this case, I'm going to swing my double bond out this way, right, away from that carbon, because I know if I swung it the other way, the positive charge would end up on a primary carbocation, which I don't want. And then the bond between the H and the I breaks, and we end up with a brand new intermediate that looks like this. Okay, and of course, we've still got I minus floating around in the solution medium. If it was just normal times, we would have that iodine, just like we showed in a previous video lecture, attacking that electrophilic carbocation, which by the way is a secondary carbocation, right, because it's bonded to two different carbon groups. And then we'd end up with the product that we incorrectly predicted. Well, it turns out there's something going on here, and sometimes this is pretty hard to remember. It turns out that right next to this carbocation is another H. And it turns out what these carbocations can do is, obviously, based on the title, this rearrangement, right? And so what happens is this secondary carbocation, right? Let's label this. This is a secondary carbocation. Is really in search of anything it can do to become a more substituted carbocation, right? Something that's a little more energetically accessible to the reaction. And the way that this can happen is through what's called a hydride shift. So in other words, this hydrogen with its two electrons that are shared right now, right? So H dot dot, or H minus essentially, is actually going to shift one carbon over to that positive charge. And watch what results. Because of that hydride shift right there, I form, from this secondary carbocation, what's called a tertiary carbocation. And that tertiary carbocation leads to the product that we see up there through the normal step that we've seen previously, where I minus comes in, attacks that electrophilic carbocation, and then we eventually go on to the product. So this particular rearrangement, right, this additional curveball right here that didn't happen before, That's something called a hydride shift. Hydride shifts are something that carbocations often undergo. You could drive yourself crazy with this, but what I'll say is if there's any kind of hydride shift that can happen that makes maybe a primary become a secondary or a secondary become a tertiary, which is the more likely one, it's probably going to happen. It really does take a little bit of practice, and it really is something that usually you're surprised by initially until you learn to predict it. What I kind of eventually started to recognize is that anywhere there was some sort of reaction that involved a carbocation intermediate, I would always be on the lookout for these kinds of rearrangements. And of course, this being organic chemistry, it's not enough to just talk about this kind of weird shift. I'm going to show you another thing called an alkyl shift, where an entire carbon skeleton kind of jumps from one carbon to another. So let's take a look at that. Okay, so here's another example of where something really surprising happens. We've got our normal HX electrophilic addition conditions here. I chose another solvent just to start to get some experience with these things. That's chloroform. And what happens is that you'll notice here that the carbon skeleton here is very different than the carbon skeleton over here, right? You'll notice that this methyl group seems to have kind of jumped from this carbon to that carbon, and in fact it did. And so let's kind of take a look at this, keeping in mind that hydride shift, and try to kind of universalize this idea of being able to kind of have a carbocation that moves around a ring a little bit. Well, what probably won't be surprising is that once you know how these things start, mechanistically they all kind of have that same look, right? You have that same door swing one of two ways. We'll kind of swing it out this way so we end up with a secondary carbocation there, at least initially. Okay, so we've got our expected secondary carbocation. I better put the Cl- in there. And now you'll notice that there are no hydrogens over here that I could shift, so it's definitely not a hydride shift, right? And I don't want to shift a hydride from here because then I'd end up with a less substituted carbon. So what am I going to do? Well, it turns out that what this reaction does is what's called an alkyl shift. What happens here is that this whole CH3 kind of comes over and does this little kind of intramolecular attack on that positive carbocation there. And just like last time, the result of this is going to give us some sort of tertiary carbocation. Where now the carbocation is right there, and this thing is a tertiary. So the thing that is kind of the common theme here is this idea of a secondary working really hard to get to something that's a little bit more substituted. And of course, then we have that product forming step where the Cl- as the nucleophile comes in and attacks that electrophilic carbon, and we end up with our product. This particular thing is not a hydride shift. This is called an alkyl shift. Right? Because it's an alkyl group, right? Just a normal carbon chain that it can that jumped over. Sure, it was just a methyl. You can call it a methyl shift if you'd like. And so this kind of rearrangement is something else that we kind of have to build into our picture here. And the one thing that really kind of complicates things for students is that any one of these carbons could have actually shifted over. And if I had picked one of these other groups to shift, I would have actually ended up with a 6-membered ring instead of the 5-membered ring. That's called a ring opening. There's also ring contractions. So there's these alkyl shifts can get really complicated pretty fast because you're actually changing the way that the carbon skeleton is built. So one thing that we'll kind of start to build into the class is this idea of mechanisms. And one of the things that is a really good step to start off with nice and early here is this idea that when you have to kind of predict, where an alkyl shift happened, well, first of all, you probably would expect it based on like a total rearrangement of a carbon skeleton. And a really good thing to recognize is that the final step of these mechanisms that we're talking about tells you kind of a little bit about where the carbocation was in the penultimate step, right? The step just before the last step. And it gives you a little bit of insight as to what kind of alkyl shift had to have happened. And of course, the first step is always the same as well. So that's kind of the way that we're going to start to build mechanisms over time here, is that we'll kind of work from the back and we'll work from the front, and then we'll try to figure out the middle. And this is just kind of the first example of a whole bunch of patterns that we'll continue to discuss.